Okay, and now we are in the computational calculi session. Thomas Love, I think you had mentioned something in that channel about a graphs language. If
Yeah,
you could just give us a brief, uh, uh, brush up of what graphs languages are. This was a new concept to me when Greg brought it up.
this is like difficult to me to say anything because I don't know anything about that. So uh, maybe I can just say what I was understand from Greg's presentation.
Okay.
And I will be very short. So Greg was talking about a different way of looking at the graphs. Not to have two sets of vertices and edges, but a set of vertices and variables as edges. So this variables as edges is a new concept. And he presented different kind of graphs, and how presentation in this style change for each of these presentation. And for start, yeah, he was talking a lot of other stuff, but this is like I think the main important. He started with a discrete graph where all the vertices are not connected with edges. So,
where
you have
connected, right?
Sorry?
Not where none of the vertices are connected?
Yeah. You don't have, it is without edges, right? Only vertices.
No edges, only vertices.
Complete discrete, yeah. The second step, like a little more complicated graph is a chain, where you have a chain, vertices, and all vertices have one child or one parent. And the presentation is very simple, right? You just create like quoted name for the variable, like in rolling. You just made up from a number. You made up this new name, and this is like a quoted vertex. And you just recursively create a new name from existing vertices, just quoted.
So what is that line that says chain of one equals let quote two equals? What does that mean?
This means creating an edge with a variable, because let enables you to create a variable.
What is one in brackets one?
I think this is like evaluated number, like for this vertex.
Specifically, we write quote D when using D as a variable versus merely D when using D as a vertex. An example in context might look like let quote D.
When D is a vertex, yeah. Okay, so in here, this is a variable, and here is a vertex.
Or is this one a variable? I mean, a vertex, because it's not in quotes.
I'm not completely sure.
I also wondered if on that line where you have the little bit of text highlighted, do those two equal signs mean something different from one another?
Oh yeah, oh yeah, yeah.
It's not like
This is
these three things are equal. It's saying like chain of one rewrites to this thing on the right or something.
exactly.
Yeah. And that equal is more like an assignment, like let this new variable that I'm calling quote two equal one,
Yeah.
and then I'm not quite sure what the, oh, those are square. Those are different.
This is one expression. Yeah. And you are creating the variable so you can use. This is, I think, variable from the previous, or from this one.
So chain of 0 equals the vertex 0. Is it that first one saying?
I'm not sure if 0.
Or the
This is like empty graph. I'm not sure if 0 is a vertex. Maybe it is.
oh.
No, if graph is empty, you don't have any vertex.
Yeah, right.
Yeah.
So that's an empty graph. It's not one.
Yeah, this is definitely empty graph. Yeah.
Okay.
So you're creating a variable from this vertex, and this variable looks at the previous vertex. I understand this in this way, right? Because you just want to create some kind of connection to previous vertex, and you just do it recursively.
Oh, there's an example right at the very bottom of your page.
Yeah.
2, 1.
And you can see here how our number is decreasing, right? This is like a names in Rollup. You just create a new name, and because edge is in a sense a link to a vertex.
Yeah, definitely an edge is a link to a vertex. Yeah, that part makes sense. I guess I'm still not clear on the integers and square brackets.
Yeah.
I'm also struggling to completely understand this.
Yeah.
I see this like creating variables, but the syntax is.
But not even, I'm not talking about the ones, not the top ones, the full angle brackets. You know what I mean?
You mean
Straight
you
up.
mean on this one?
No, to the right. Yeah, those ones. Yeah, what does that mean?
This is probably like a val, right? Because you want to reify this variable to really what it is, right?
Okay.
But I'm not sure from where this one is coming from.
Yeah.
But in next example, he creates more complicated graph which has cycles. You know.
Yeah.
Oh, this is like a chain with a cycle. Yeah. And then another more complicated graph is what is he called complete, where every vertex is connected to every other vertex. And so this is like the most complicated graph, because you have all the paths from all the vertices, right? And the definition is still only one line.
Okay, hold on. I'm starting to get a better sense. Can we go back to the list one or whatever it was called, the chain? So I think he's giving 3 examples. Like that first one is the chain with 0 nodes, the second one is the chain with 1 node, and then the general one in the end or something.
Yeah. And this is not example, this is like the definitions.
Wouldn't that chain 0 be the node with the single node with no edges?
Yeah, exactly. Yeah. Oh, with no edge.
Saying chain 0 which we're saying is empty, I think. Maybe
Yeah,
zero.
this is the number. This is the number of vertices.
Okay. Okay. I got you.
So this is like a definition of a function, because you can say, you know,
Yeah.
for chain
I understand it now.
and the definition is recursive, because here you recurse one vertex less, and then back to the first one.
So under the cycle, it says the cycle graph of n vertices and n edges simply creates an additional edge from the end of chain of n back to the beginning. That makes sense, right? You've got a long chain, you just glue the ends together, now you've got a cycle.
Yeah, yeah.
So I was just trying to look at that line, cycle of n, because that one looks straightforward enough that I thought I might be able to parse it. So like we've got the angle brackets, and then inside there's chain of, oh yeah, it's not recursive directly this time. It goes back to chain instead of cycle itself. So I wondered if those angle brackets, does that mean like make an edge or something, or?
I'm not sure.
Yeah.
I'm not sure what does it mean. These brackets, right?
Yeah, yeah. The complete graph.
Is this like a tuple? Maybe, I'm not sure.
Yeah. Is the syntax defined anywhere? Like what did we scan over at the beginning?
Well, he didn't give the syntax for these brackets. But
What's the title of this document?
oh no! We have the syntax for the brackets.
Oh, nice.
I
Okay.
missed it.
Okay,
Oh.
0, the empty graph, or just empty, v par g, g with a vertex v adjoined, or adjoined v to g. Oh, wow.
Yeah, this is like a par. And the product is somehow merging two graphs. And with the let, you create.
Stand for V and G.
This is like a variable, right?
Okay, so the brackets must mean like the graph of one, where one is just the vertex. Brackets might mean the graph of one vertex.
You're talking the square brackets, Jay, or the like?
Yeah, square
This
brackets.
part.
Yeah, or even just the one above. It says let X stand for V and G. So G must be a graph.
Yeah. Yeah.
Oh, G is a graph. Yeah, that makes sense.
And here, G is a graph, what V is a vertex.
G with the vertex V adjoined. Oh, that seems like it's sort of underdefined, right? Like that could be a join. Oh, no, it's not connected with edges. It's just a vertex that's part of the graph.
Mm.
Yeah, okay.
I was thinking that both of these things are graphs. Okay. They're not.
And then what does juxtapose mean? Is that like connecting the edges between nodes, or?
He was explaining this. This is like a merging. And you must be careful to not merge the same variables, right? This is like joining two different graphs. If you have two graphs, you can combine it.
Yeah.
Yeah, but there's like a few different ways you could do it. Like you could distribute nodes to connect to other nodes. Or I mean, so the adjoint one is probably just taking two graphs and then calling it a new graph.
Somewhere, I think there is a definition for all of these constructs. Yeah. So yeah, here is the definition for all of these constructions.
Oh, well, that clears it all up.
Yeah.
Is this the syntax rules or the semantic rules? Because I don't know if it's actually explaining how the reduction works.
I think A couple
So
lines
reduction,
down.
yeah, reduction is only in.
There we go.
Where?
The rule for juxtaposition says that simply juxtaposing two well-formed graphs
Oh, sorry.
That's okay. No, that's no problem.
Okay.
I don't even know if that's what we were looking for. Juxtaposing two well-formed graphs results in a well-formed graph. A careful account will observe that the dependencies of the two graphs must be disjoint. Okay, that's what you were saying, right? The dependencies must be disjoint.
Yeah, and dependencies are edges, I think.
Oh.
And they must be disjoint. And Greg was saying that you always want to have edges disjoint. And yeah, I was reading some papers about bigraphs, and they have this similar notion of vertices, and one graph for vertices and one graph for edges, and they must always be disjoint. So there is some kind of similarities. And I want to find the reduction. There is some. Oh, no. He was explaining he has an example of graph of reductions for lambda calculus. Mm. And I was playing with row calculus. So here are the example for lambda calculus, and here is the reduction, right? But I'm not sure what does it mean to. This V is set of vertices, and you want to get the reduction on T, and then I'm not sure what this doesn't mean. So we're selecting.
What was his intention for defining it this way?
So this is like an encoding of lambda calculus in the graph, and you have like a nice language to express the reductions with this graph language.
Mm.
And
so
he was
the idea that I can like think up an arbitrary lambda calc term and express it in terms of some nodes and edges, and then from that graph you can like visually identify the reduction rules and do some rewrites.
Yeah. I'm thinking that, and Gary was explaining this. If you can store the reductions like this inside the graph, you can write like better query language on graph to search for specific reductions, right?
To search for reductions. This is the problem of like finding reductions.
Yeah, I mean finding programs. If you can say I need this kind of part of the graph, and you're searching really for a program.
Yeah.
Because graph is in that sense AST, and you're searching the right reduction.
Hmm.
And yeah, he was saying that you can with this you can build better like graph query language, like better than, for example, what is called Neo4j query language.
Yeah.
I was looking at different query languages, and you always have this situation that you don't have a recursive relation between vertices and edges. So you're specifying, I have this vertex and this property of this edge and this property of this edge, and you're specifying like the whole path, but you don't have a recursive relation to specify. So
I was thinking about GraphQL while you were going over this, and that stitch wait, which one was it? Go up a little bit. One of the things in that list sounded like stitching in GraphQL, which GraphQL is a graph query language, sort of.
oh, you mean GraphQL as like a Facebook framework for API?
Yeah.
But this is not a query language, right? This is like just a very simple API specification. But you cannot query anything because you have very simple syntax.
I don't really know much about GraphQL. I thought that's what the QL stood for, though.
Yeah, query language. Yeah, GraphQL. The idea is that you define some types, and then you can they define how you can query over them.
Yeah, but you're not specifying. I mean, you're just specifying how they are connected, parent child. But you cannot search anything. So in that sense, this is like a misleading title.
What do you mean you can't define how to search, or you can't search on it?
I mean, it's not part of the language. You cannot say, oh, okay, I'm searching something that is where my well, you have support for function, right? And that's it. But they're not specifying how to search. This is not part of the language. In that sense, I'm saying it's very simple. It's too simple to be the real.
So, Tomislav, are you saying that like it allows us to express queries, but doesn't provide like an algorithm for efficiently executing those queries?
Well, it's not built to query, because you are specifying the exact schema, and you have limited support for specifying like query. But this is not a part of the language. You just have a function. You cannot do anything else, because you're constrained with the types, and types are very, very simple. You're just saying, okay, I have this type which has these properties, and these properties have these types, and that's it.
So yeah, I guess what Josh is saying, like you can specify the schema and you can specify specific values for the attributes, but you can't specify how to find them.
Yeah. I mean, you can specify how to find them in only one way. You just wrote, what do you want to get from the server. In that sense, this is like a query, because you're querying only part of the whole type.
So you could sort of create graphs as types in this thing.
I mean, types are represented as graphs, right? Because you can reference, you can have property that has the same type as the defining type. You can have self-recursive type. That's completely fine.
Yeah, that's something you can't do in like SQL either, right?
Can or cannot?
Cannot. Like have a self-recursive type.
But yeah, you can. You can self-reference table, right?
Yeah, you can self-reference a table, but in like some kind of like migration, if you wanted to, trying to think of how you would express this in SQL. Like if you want to say on this table, all the like managers, you have a list of all the managers, and you want to figure out all the managers that manage themselves. Like how would you write that as a SQL query?
Oh, when you want to query, not the story, not like the model.
Yeah, not the store, but the query.
Yeah. The SQL is doesn't have like a native support for recursion. So you can use like a common table expressions to do something like that.
Yeah.
And yeah, I was using the CTA for this kind of stuff. Yeah.
You're using what?
This common table expression. When you say with something, you first you write the first query when you start the recursion, and then you have union with all the other results. So you have like a recursive query to query this recursive structure. Yeah, and I'm trying to build something similar, and I'm interested in this stuff, stuff because I want to write. I want to build this query language on top of this, for example, GraphQL or SQL. Because now I want to convert this query, the graph query language, to recursive this CTA SQL query. The next speed, I will definitely show you what I have done. Yeah.
Do you have a repository going for this, or you're just starting out?
Well, I don't have in this state. I don't have anything to show. So, yeah.
Thinking about it. Yeah, I mean, I would definitely be interested in this too. This coincides a lot with what I do at work, anyways. So maybe I could
nice.
Make a connection.
Okay.
I was wondering if you can embed simple type lambda calculus, so you could do like finding programs that goes from one place to another by searching the graph, or is it the wrong intuition?
Yeah. That would be interesting, and even more because if you can encode all of this reduction, right? You can differentiate between sort function and shuffle function, right?
Yeah.
Because you know all of these reductions, and I think this is like in the heart of behavioral types, and you want to say what kind of reductions are semantically the same or behaviorally the same.
So you would have a ability to compare functions, right? To say if they are equal. That's cool.
Yeah. And you definitely can do this if you encode all of this AST in graph, but having the really nice language for this is something that it doesn't exist now. So
cool.
Tomislav, it hasn't existed before. Why do you think it exists now? Because of the row calculus ability?
This is not really connected to row calculus.
Okay.
It is just a representation of graph in a different way. When you don't have set of edges, you have variables. So you have another language for expressing graphs, and later this is where.
Okay, but then why do you think this hasn't existed before?
Well, Greg was saying that in graph theory they don't represent edges as variables. They don't represent graphs as a recursive structure.
Okay, I got you. That's what I was looking for.
And of course, you can encode not only the reductions. You can encode the syntax of the graph inside the graph, so you can have a completely recursive structure.
I can't even imagine how you do that.
I'm thinking that you're encoding these operations on graph inside the same graph. So,
but I mean, everything is still just a node and edge, right? Like there's no information within nodes beyond some number.
Yeah, node and variables. Yeah.
Mm.
And this part I'm not sure how to interpret. I was working on this stuff, so maybe you can help me to define this one, because I was looking at the lambda definition, and I was trying to make for raw calculus.
Mm.
But I'm still not sure about these two lines, because they are the reductions, and this is the part, right? So the first one is the real reduction when we have send and receive, which seems like very simple to just apply the COM rule and then reduce whatever is left in continuation. But I'm not sure for all the other part what to do. This means that we are extracting the vertices from this reduction.
Okay.
And I'm using the join, receive join here to extract both vertices. So I'm not sure if this is correct.
T and U. And what's the reduction for, that's the process T is sending process T. What does this line mean? Up above, it's like the middle line.
This one?
Yeah.
This means that the reduction of eval.
Of a what?
Of eval.
Eval, like dereference.
Dereference.
Mm. So it's just defining it. It's not like sending.
Yeah. It's just a reduction of this term is just I'm not sure how to say what it is. This arrow means reduction.
Reduction.
But is defined from these rules. I'm not sure also how to interpret this one. What does it mean to have this kind of definition? This is like a unit.
So would I be far off if I thought of this as sort of a process language of graphs of processes? Obviously, I've said the word processes twice, but is that where all this comes from? The process calculus?
I'm not sure. I think this is not related to process calculus.
Really?
I think
okay.
I think that
kind of the other way around, right here, right?
Yeah. I think that in this way you can encode different process calculus or something like that.
Yeah, you can encode a process calculus as a graph or a graph reduction.
I see.
So Tomislav or Jay, I guess maybe the idea is like this isn't specific to process calculi, but it's a general purpose tool / framework, and we are now looking at its application to process calculi.
Yeah, and how to encode the reductions inside this graph. Yeah.
So this is a silly question, but it looks like all those like 6 or 7 lines there, are they just replacing the RED function with an up arrow?
Yeah, even like this one.
Sometimes it gets angle brackets. Yeah.
Yeah, and I was using the same thing as for lambda.
Yeah.
And abstraction, we just do nothing, right?
That's
I'm interpreting this as, you're just storing the exact term. There is no reduction, so I'm not sure. Is this mean to do nothing or store nothing? Or
Yeah. Like, is
because
there a
we,
side effect to that?
sorry,
Do you mean like, is there a side effect to that reduction, or?
I'm thinking that this is the definition for reduction, graph of reductions. So if you just have a variable, you don't reduce anything. You're just, I don't know. If you have graph of reductions, I don't know what do you store in this situation, because you don't have reduction, you just have a variable. So maybe this is like a leaf, or I mean, like a vertex.
Mm. I actually need to head out, but I will definitely look more at this. This is really cool. All right, see you guys.
See you, Jay.
Yeah, Jay.
I've got a roll kind of soon too. Tomislav, I have a really basic question though. Who wrote this doc that we're looking at here? Is this your notes, or is this Greg, or something different?
Oh, this is my notes.
These are your notes. Okay, cool.
Yeah, I was just
based on Rcast.
sorry.
These are your notes based on that Rcast.
Yeah. Greg was publishing this link here.
Nice job on note taking.
Yeah, for real.
No. This is like the whole document. Greg posted the whole document. I was just copying this part.
Oh, okay. I didn't see that.
And I was just copying the lambda calculus definitions and try to define the row calculus. And the whole document is Greg's. So.
Oh, the row calc is you though. This is your attempt at doing it for row calc?
Yeah, just this part.
Oh, interesting. Okay, I see.
But most of this is just a copy of lambda calculus. So I didn't.
The part down below about categories.
Yeah.
Oh, that's a new section.
That's a new section. Yeah. The whole document is super interesting. You know. So.
Yeah.
I don't remember him making this document available. Did he do that along with the Rcast?
Yeah, it's here.
Oh,
Here,
okay. Thanks, Tomislav.
No problem. Greg was mentioning this a long time ago, so I was waiting for this. You know, so this definition of graph.
Yeah, he mentions a lot of papers on there that I hate to be the only one that bugs him and the rest of the Rcast team to get the links up there, but maybe we should all start pressing them a little bit, because I'd usually like to see those papers when he mentions them, but
Yeah.
you know, a day later I've forgotten them.
You've got pretty direct access to Isaac. He might be able to make that happen.
Okay.
I mean, he's on all those Rcasts, right?
Yeah, lately he has been, yeah.
Yeah. Cool. All right. I've got to roll out for today too, guys. I want to talk more about this though. It seems awesome.
Yeah, this is getting interesting.
All right.
Fine. A couple of questions, but maybe I will store them to the next session.
Yeah, sure. I want to
one quick one. Do you know if it is somehow related to the stuff that people in Haskell have done about algebraic graphs?
When you say algebraic graph, I'm not sure what it is, but it's definitely definitely algebraic representation.
Okay, cool. There was some paper about this stuff not so long ago, but yeah, I'll take a look at the.
There's the links. Yeah. Post the links.
Cool. And yeah, did you have an experience with this stack edit IO thingy? It looks awesome to make notes about the stuff like mathematics.
Oh yeah, I'm using this the first time. I was just converted. I noticed this Greg's definition, Greg's document is in version 4, and I converted in version 5. I'm not sure. They have two different versions, and they are completely like separated. So, but yeah, I like this representation. I was thinking that this stack head is only for Markdown, but it seems that it works for LaTeX or something like that.
Yeah, it looks like LaTeX. I've pasted link about algebraic graphs on the chat.
Nice. Oh, on the Discord, please. Because
Sure.
here in the Zoom, you lose all the stuff.
Disappeared. Yeah, when I get the proper window, I paste.
And I wanted to ask you about your repository, about Type Classopedia. If you can just, scroll to the repository and say something, what do you have in the repository? Because there is a lots of interesting stuff, and the whole hierarchy of, type classes and.
Yeah, there's a lot of, yeah. I would glad to share with you give some tour or something like that about the stuff.
Yeah.
But do you want this to happen today?
Well, if you have time now, that will be great. We can stop recording and record just your presentation.
Okay. Do you want to do that now?
Please.
I'll stop recording.